Hello, my name is Dane Swanser, and today we will be doing an FRQ problem that relates to force going down a ramp, angular velocity, and angular acceleration and energy. So, the question is, a wooden wheel of mass m consisting of a rim with spokes rolls down a ramp that makes an angle theta with the horizontal as shown above. The ramp exerts a force of static friction on the wheel so that the wheel rolls without slipping. On the diagram below, draw and label the forces, not components, that act on the wheel as it rolls down the ramp, which is indicated by the dashed line. To clearly indicate at which point on the wheel each force is exerted, draw each force as a distinct arrow starting on and pointing away from the point at which the force is exerted. The lengths of the arrows need not indicate the relative magnitude of the forces. Okay, so first we're going to start with our, I'm just going to take it away for a second as I write on it. We're going to start with our force of gravity, or mg. Then, pointing away from the ramp, we're going to have our normal force, Fn. Then, going up the ramp and away from the wheel, you're going to have our force of static friction. So that is our free body diagram. Now, then it asks, as the wheel rolls down the ramp, which force causes a change in the angular velocity of the wheel with respect to its center of mass? So, that's saying, what causes change in angular velocity of the wheel? Well, that's an angular acceleration problem, pretty much. And for that, we need to ask ourselves, what is causing net torque on the wheel, because that is what affects our angular acceleration. Well, the only thing that could cause net torque on our wheel is the force of static friction. So that would mean, excuse me while I put it away to write, Fs causes a change in angular velocity due to the effect of net torque on the system. Alright, so we've done A1 and A2, and now we go into section B. For this ramp angle, the force of friction exerted on the wheel is less than the maximum possible static friction force. Instead, the magnitude of the force of static friction exerted on the wheel is 40% of the magnitude of the force or force component directed opposite to the force of friction. Derive an expression for the linear acceleration of the wheel's center of mass in terms of m, mass, theta, and physical constants as appropriate. So, for that we need to look at, for our angle, the force of friction exerted on the wheel is less than the possible static friction force. So, just to organize our thoughts here, are the magnitude, or mag, of force of static friction on wheel is 40% of force directed opposite of force of static friction. Alright, so for that, now we are going to start with kind of labeling our system here. So down the ramp, we're going to have the x in the positive direction, and up here, with our force normal, we are going to have y in the positive direction. So, oops, sorry, okay. So, now that we've established this, we can see that the component of objects' weight down the ramp is equal to mg sine theta, because we know that's our equation, which leads us to, well, the component of object's weight down the ramp. So that would be Fs is equal to 0.4 mg sine theta. Alright. That will help us solve for a linear acceleration. So, then we need to look at our net force in the x direction, because we know that is our total, and it's 40% of that in the x direction is equal to MAX. So, then we have to subtract the two. We have to subtract our, sorry, I'm just going to start writing over here. Actually, I'll put it down and then show it to you. So, mg sine theta minus minus 0.4 mg sine theta is going to be equal to ma, mass times acceleration. Okay, so we can see A is equal to, because that will help us find our equation up here. Let me just show you what I wrote here, down here at the bottom. It's our equation. So then we have A equals 0.6 mg sine theta over m. Because this equation here helped us find 0.6 mg sine theta. That's what we got that from. Now, if we do this equation, we plug all our numbers in, we should get A equals 0.6 g sine theta. And that is our answer for section B of our FRQ. So, we're going to erase this here. And we're going to look at section C. So, sorry, let's not have that messy. So then C is, in a second experiment on the same ramp, a block of ice, also with mass m, is released from rest at the same instant the wheel is released from rest and from the same height. The block slides down the ramp with negligible friction. So, and then it asks, which object, if either, reaches the bottom of the ramp with the greatest speed? So, let's look at that. Well, first we need to examine the forces acting on each of our objects. So, forces. For our block, we have no frictional force. Okay. But now, for the wheel, we have our force of static friction pulling it up the ramp. Okay. Now let's look at it in terms of energy. At the top here, we have our potential gravitational energy, E.g. I'm going to leave that there so you can get it in case you didn't see it. Okay? Now, then at the bottom we have our kinetic energy, which, for the block, is 100% translational because there's no force of friction acting on it. But for the wheel, we have some of both. But we know that because it has some of both, and it has static friction, it cannot be 100% translational like the block is. Well, because it is 100% translational, the block will reach the bottom first, because it has no friction acting against it. That should be the answer for problem C. And it asks us to explain that in part 2 of C. And that is the answer, and that is the end of our FRQ problem. Thank you for learning with me today. I enjoyed learning with you.